This is part 2 of the summary of the topic of motion for Year 10 Science. And this video will look at graphs of motion. So I'm going to begin with this graph. So the y-axis here, let's call this distance. Okay, in meters, let's say. And the x-axis is time. Usually in physics and science, we use time as the x-axis, let's say seconds in this case, because time is usually an independent variable. Independent variables are variables that change. So time is changing. Let's suppose we're measuring distance. Suppose I'm standing watching you in a car drive from point A to point B, and I measure the distance it takes for you to cover in a certain amount of time. So let's suppose time ticks as normal, as follows, from 0 to 6 seconds. And I stop my timer here at 6 seconds, and you're covering a distance of, I don't know, 1, 2, 3, 4 meters. So you cover total distance of 4 meters in that 6 seconds. And I'll draw a graph like this. So I'm making this on the spot. It might not be realistic, but anyway, just to help you out. Like that. Now the graph makes sense. Really think about it intuitively. As time goes on, your distance increases, and that's what I'm seeing there in the experiment. So over time, the distance increases. So that's a straight line there. How do you go from this distance to a speed time graph, let's say? Now, here's what you do. Time always stays the same. Okay, time's from 0 to 6 seconds. That's not changing. Okay, all we're doing is really converting between distance and speed. So that time stays the same. The x-axis doesn't change. It can't change. It won't make sense for it to change. Six. So that doesn't change there. However, we need to work out how to get the y-axis here, which is speed. Let's call this meters per second. Now we know that the formula, you need to go back to the formula for speed. V is speed, and that's distance d divided by time. So something divided by something, well, if you think back to maths, that means you need to find the gradient, the rise over run. For the graph, rise over run. The rise is this. Think of someone is rising up from sleep. They're sitting up, right? The run is this, right? You run along the x-axis, you run along the ground. And let's plot the speed over time. So look at each of these data points. Now the scale isn't that good. I'm going to stop at, now for drawing the graph, I'm going to stop at 4 seconds. I know there's up to 6 seconds, but I'll stop at 4 seconds. So for the first set of points here, so 0, 0, there's nothing happening. Right, there's 0 there. Nothing's happening because 0, 0 and 0 is nothing. 1 divided by 1. Okay, rise, which is 1 divided by 1. 1 is 1. Next point, 2 divided by 2 is 1. So that 1 stays there. 3 divided by 3 is also 1. 4 divided by 4 is also 1. So what we see here is the speed, put some more numbers there, is a flat line. It's constant. Constant over time. Constant means it's fixed, okay? You're not accelerating or anything. Let's say your foot's off the pedal once you accelerate. So beforehand here, you're probably accelerating, and then you take your foot off the pedal here. At this instant here, time t equals 0. When I start my stopwatch, you take your foot off the pedal and you're cruising along, and your speed is the same. It's 1 meter per second for the 4 seconds, let's say, ignoring these two here. So that's that. What about acceleration? Well, once again, time stays the same. 0, 1, 2, 3, 4, 5, 6. Okay, acceleration, call it A, is meters per second squared. We know that acceleration A is the rate of change of velocity, is the change of velocity over the change in time. However, if you look at that graph there, constant speed, there's no change in velocity. Velocity, the speed, is the same. Okay, for now, ignore directions. Let's just look at speed. Okay, velocity without a direction is speed. A flat line. Now, the gradient of a flat line is zero. There's no slope. The velocity is not changing in this case. So therefore, you have a flat line on the x-axis. You can put numbers here if you want, but that's the idea. And that's how you go from distance time to speed time to acceleration time. A very simple example. I'll summarize. So suppose you're in a car and I'm watching your motion, observing your motion. I mark 2 points on the road, one over here, one over here. You accelerate before this point here, and I start my timer at time t equals 0. And then I stop my timer at t equals 6 seconds. Okay, well, let's say t equals 4 seconds. When I graph your distance time graph, it'll look like this, something like this. Okay, a straight line, uniformly increasing in a linear fashion, in a straight line fashion. 1 meter is covered in 1 second. 2 meters in 2 seconds, 3 meters in 3 seconds, and so on and so forth. It's a linear relationship. So therefore, my speed will be constant because speed is v, velocity. Is v, and that's distance divided by time. That's the rise of a run in this case, because d divided by t is rise of a run. For each of these set of points, I'll work out the speed. It simply gives me 1. It's a flat line. And now the acceleration will be 0 because acceleration by definition means your speed's changing. If the graph was like this, then you will have an acceleration time graph. However, you'll get a flat line because the speed is constant and the acceleration will be 0.